For a problem like this, where you're supposed to be matching a recursive form with an explicit form, like you see here, so recursive are all up here at the top, and explicit are all over here on the left-hand side of the page, I would go forward and actually, or kind of take a middle step, and actually write out the sequence first, and then match it up to the correct explicit form. So for this one that's up here at the top, it says that the first term is 6, and that in order to get to the next term after 6, we multiply by 2. So if I was going to write the sequence, it would be 6, comma, the next term is 2, I'm sorry, multiply by 2. The next term is 12, the next term is 24, the next term is 48. For the middle column, my first term is 5, and I'm adding 2 every time to get to the next term. So 5 plus 2 is 7, plus 2 is 9, plus 2 is 11, so on and so forth. This last one, the first term is 3, and I'm multiplying by 2 every time. So 3 multiplied by 2 is 6, multiplied by 2 is 12, multiplied by 2 is 24, so on and so forth. If I can correctly match that sequence to these explicit formulas, then I should be good to go. Notice that these first two the first one is geometric because I'm multiplying, and the last one is geometric because I'm multiplying. This middle one is arithmetic because I'm adding every single time. So you can kind of start to match up certain ones because if you look at these sequences or equations over here in explicit form, this first one is a geometric because I'm multiplying. This next one, geometric, I'm multiplying. This next one I'm adding, that's an arithmetic sequence. This next one I'm multiplying, that's geometric. This next one, adding, arithmetic. And the last one, geometric, because I'm multiplying again. So for this middle column with arithmetic, the only options are either this function right here or this function right here. So let's match that one up first. So we need to decide, remember that there's two different forms you can write it in. You can either write it in explicit form like this, f of n equals f of 0 plus d times n, or you can write it as f of n equals f of 1 plus d times n minus 1. So if we did it using the first one, we would need to go back to the initial term or the 0 term. And right now we have 5 to start with, and we're adding 2, adding 2, adding 2, adding 2. So to go back to the initial term, we could subtract 2. 5 minus 2 is 3. So 3 is our initial term, and then from there we're adding 2 every single time. So if we can look at both of these two arithmetic equations, the one of these that matches up is the one that has 3 as my initial term, like this, and I'm adding the common difference, which is 2 n times, and that matches up right here. 3 is my initial term, and I'm adding the common difference, which is 2 n times. So I would put a check mark right here. Oops. Put a check mark right there. This other one, all right, this says the initial term is 2, and I should be adding 3 n times, but that would be backwards. So notice that that one is not a true. I'm going to put a check over here that says that that does not match any of the equations. So that takes care of those two. Arithmetic is handled. Notice there was another form we could have written it in, but none of those two, or I should say neither of those two arithmetic sequences we were just looking at had this n minus 1 in them, so we didn't need to look at that form. Now let's look at this geometric one. So for geometric, you can write your functions as f of n equals f of 0 times r to the power of n, or you can rewrite it as f of n equals f of 1 times r to the power of n minus 1. So notice that we have some combinations. I'll highlight the ones we're looking at that are geometric. So this is geometric, this is geometric, this is geometric, and so is this one. Notice that some of them have the n minus 1, and others of them just have the n. So we need to check both of them for these to make sure that we don't accidentally skip one that we should not skip. So if we start at the first term here, all right, so let's look at this one right here. We're looking at f of n equals f of 1 times r to the power of n minus 1. So if we start at the first term is 6. But if I look at these highlighted ones, none of these have a first term of 6. So obviously I'm not looking in this form to match this sequence correctly. So let's look at the other form. The other form says f of n equals f of 0, which is the initial term, times r to the power of n. Well, here I have 6 as my first term, and to get to the next one, to get to the next one, to get to the next one, I'm multiplying by 2. So to go backwards, to go back, I would divide by 2. 6 divided by 2 is 3. So if I plug that into this equation, I have 3 times r, which in this case is 2. I'm multiplying by 2 every time. I have 3 times r to the power of n. So let's look. That's not it. Oh, I think I found it. This is 3 times 2 to the power of n. So 3 is my initial term. 2 is my common ratio, and n is the exponent. So this is a correct match. So let me erase that one because we found the match for that. Then for this last column, we can use these exact same equations again. Oops, didn't want to erase that. There we go. We can use these exact same equations again for this last column. So let's look at the f of 1 first. Let's see if either one of these n minus 1 functions matches. So if we start at f of 1, which is 3 in this case, the first term is 3, and my common multiplier is 2, I can say that this equation would be 3 times 2 to the power of n minus 1. My first term times my common multiplier to the power of n minus 1. So 3 times 2 to the n minus 1. Nope, not this one. Oh, I think I found it. 3 times 2 to the power of n minus 1. So let's go ahead and check that box and say that this is a match. Now, just because we found one match doesn't necessarily mean that we found all the matches. So we had easily been able to see that those other ones didn't match this one, for example. But what if one of these ones also matches? I think it's obvious that this one doesn't because it has an n minus 1. So that one would not be correct. We already found the equation that has the n minus 1. But what about this one? Is this one a match for this equation as well? Because maybe it's just written in a different form. So let's check it out. If in this one I decided to go back to the 0 term. So here I'm multiplying by 2, multiplying by 2, multiplying by 2. If I wanted to go back to the 0 term, I would divide by 2. Well, 3 divided by 2 is 3 halves. That kind of answers our question. If the initial term is 3 halves, the first term here, or the first number here, should have been 3 halves. But neither of these has that, so obviously these are not correct answers for our problem. So we have found all of the matches that correctly match up together. And so one thing you need to make sure of is wherever you didn't put check marks, make sure that you have them saying that they do not match. So the first one does not match anything, so we should put a check over here to say that it does not match. The second one we had, the third one we already know it didn't match, the fourth one we have, the fifth one we have, and the last one did not match either. So that would be a correct final answer for this problem. And maybe it takes a little bit longer to do it because there are ways to go directly from recursive form into exponential form, but this is just one way to do it where it keeps your thoughts all nice and organized and you don't have to worry about misremembering something or forgetting something. You can go based on concepts.